The Newton search method. In this method, the function we wish to optimize is assumed to be smooth and has second order derivative. The idea is to select an initial trial point and then approximate the function f of x in the vicinity of x0 by a quadratic function. Using Taylor's formula, suppose the function f of x is approximated by the following quadratic function: fq of x equal to f of x0 plus x minus x0 times f prime of x0 plus half times x minus x0 squared times f prime prime of x0. We determine the point x1 that optimizes fq of x by this: x1 equal to x0 minus f prime of x0 divided by f prime prime of x0, provided f prime prime of x0 is not equal to 0. Now, using x1 as the next trial solution, we obtain x2 equal to x1 minus f prime of x1 divided by f prime prime of x1, provided f prime prime of x1 is not equal to 0. Continuing this way, we generate a sequence of trial solutions given by this: sk plus 1 is equal to xk minus f prime of xk divided by f prime prime of xk for k equal to 0, 1, 2 and so on, provided f prime prime of xk is not equal to 0. This sequence of trial solutions is expected to converge at the optimum solution. Stop criteria. We can use any of the following criteria to terminate the process. 1. F prime of xk equal to 0 and f prime prime of xk is less than 0 in the case of a maximization problem. 2. F prime of xk equal to 0 and f prime prime of xk is greater than 0 in a case of minimization problem. 3. Absolute value of sk plus 1 minus xk divided by max of epsilon 1 absolute value of sk plus 1 less than or equal to epsilon 2. 4. Absolute value of f of sk plus 1 minus f of sk divided by max of epsilon 1 absolute value of xk and absolute value of sk plus 1 less than or equal to epsilon 2. The algorithm. Step 1. Set k equal to 0 and select an initial trial solution x0. Step 2. Compute f of xk, f prime of xk, f prime prime of xk, and then sk plus 1 equal to sk minus f prime of xk divided by f prime prime of xk. Step 3. Is the stop criterion satisfied? If yes, stop, because sk plus 1 is the optimal solution. If no, set k equals to k plus 1 and return to step 2. Remarks. Remark 1. The Newton's algorithm may not converge if the initial trial solution is far from the true optimum. In fact, Newton's algorithm might even fail no matter how near the trial solution is to the true optimum. Remark 2. The sufficient condition for the Newton's algorithm to converge is that f of x must be convex. Remark number 3. Given the interval from A to B containing the optimum solution x star, the Newton's algorithm will converge at x star no matter where the initial trial solution is in the closed interval AB, if the following conditions are satisfied. 1. F prime prime of x exists and does not change sign in the interval AB. 2. F prime of A times F prime of B is less than 0. 3. F prime prime of x is not equal to 0 in the interval AB. 4. Max of absolute value of f prime of A divided by f prime prime of A and absolute value of f prime of B divided by f prime prime of B is less than or equals to B minus A. Example 4. Solve the optimization problem. Minimize f of x equal to minus x exponent minus x. Solution. First, let us differentiate our function f of x to obtain f prime of x equal to x minus 1 in bracket times exponent minus x. Please, we apply product rule here to obtain this. We also find the second derivative, that is differentiating this function. F prime prime of x is equal to 2 minus x in bracket times exponent minus x. We recall the sequence of trial solutions is generated by the formula sk plus 1 equal to xk minus f prime of xk divided by f prime prime of xk. This is equal to xk minus, put in the expression for f prime of xk, which is this, divided by this. Clearly, exponent minus xk will cancel exponent minus sk here, so that sk minus this will then give us sk plus 1 minus sk divided by 2 minus sk. Our result is summarized in this table. This is k starting from 0, 1 and so on. This is our sk. If we take our initial trial solution x0 to be 0, so x0 would be 0 here plus 1 minus 0 divided by 2 minus 0. That's 1 all over 2. That will give us 0.5. F prime x0, when you put x equal to 0 here, that will give us minus 1 times 1, and that is minus 1. F prime prime of 0, when you put x0 here, 0 here, that will be 2 minus 0, which is 2, times exponent 0, which is 1. 2 times 1 will give us 2. Now if we put k equals to 1, if you put k equals to 1, that will give us x2 equals to x1 plus 1 minus x1 all over 2 minus x1. So x2 is this, which will give us x1, which is 0.5. Remember, this is our x1, 0.5, plus 1 minus 0.5 is 0.5 divided by 2 minus 0.5, which is 1.5. So when you work this out, that will give us 0.833. F prime x1 will give us this. F prime prime x1 will give us this. Similarly, f prime x2 will give us this. F prime prime x2 will give us this. So if we continue, by the time we get to k equals to 5, you will notice that here that f prime x5 is 0 and f prime prime x5 is 0.368, which is greater than 0, meaning that we can stop at this point. That is, f prime x5 is 0, f prime prime x5 is greater than 0, and our x5 is 1.000, meaning that the optimal solution is this, that x star equals to 1.00 is the optimal solution, and our function value at that point is equal to minus 0.368.